So folks, what we're going to start on today, see how far we get today, see if we can cope with the temperature in the classroom, maybe we'll warm up shortly. We're going to start on the halogenoalkanes today. Okay, we have done alkenes. You should know all of the kind of characteristic reactions of alkenes. You should know the mechanism. What was the mechanism that we did for alkenes? Go on, Leanne.
Free radical addition?
Not quite.
Oh, it was electrophilic.
Electrophilic addition, exactly, yeah. So free radical is free radical substitution for alkanes.
Oh, okay.
Yeah, so free radical substitution we've done, and electrophilic addition. Okay, there is another mechanism that comes up in this topic as well. Okay, there's only 3 mechanisms for the whole of Year 12 chemistry, and we're almost done with them already. Okay. Oh, close the door. Not the singing, please. Nobody likes the singing, apart from primary students, who I'm sure love it. All right, so we'll look first, since we're doing halogenoalkanes, we'll look at their nomenclature, how to name them. Okay. So, what is a halogenoalkane? Well, I think you probably should be able to work that out for yourselves by now. Okay, but it's essentially they are alkanes, but they have one or more atoms replaced by a hydrogen. Not a hydrogen, a halogen. A hydrogen atom replaced by a halogen. Egypt. So there's one right there, trichloromethane. It's actually had 3 hydrogens replaced by 3 chlorine atoms. Okay. They can contain more than one type of halogen. For example, a class of chemicals called Cfcs, which you might have heard of. Cfcs are the chemicals that were responsible for damaging the ozone layer. Scientists now believe that very slowly, because CFCs have been banned in every country of the world, scientists do believe that the ozone layer is starting to repair itself. Okay. Do remember though that the ozone layer, damage to the ozone layer, is different from climate change. Completely different. Okay, so that one there, what is that called? Oh, Chloro Ethane. So chloro, because there's one chlorine, but pentafluoro, because there are 5 fluorines. Yes, I've maybe got a question?
So you wouldn't have to specify, like, there's 3, like you wouldn't say like 3 trifluoro, because like there's 3 fluorines on the first carbon. There
are 3 fluorine atoms on the first carbon, but then again you could look at it the other way and say that there are also 3 carbons on the 3 fluorines on the second carbon atom. Doesn't matter how you arrange that chloropentafluoroethane, there is only one possible version of it, so you don't actually have to have numbers with it. But if there was a hydrogen as well, then you would end up with having multiple versions, and you'd need lots of numbers. Okay. So some halogenoalkanes are actually useful themselves, but many are good intermediates. They're good intermediates to produce other molecules. Huh? Yeah, but you see, liking it and getting it in your head are 2 different things completely. Yeah. I had. Has anyone seen The Little Mermaid? Yeah. For some reason, the other night I had the song "Under the Sea" in my head. And I was like, I think my wife and I were doing the washing up, and I just like every 10 seconds I kept humming it, and she's like, "Can you shut up now? Can you just stop, please?" You can imagine how annoying I am, really. All right, so I'm going to change the slide, folks. Let's actually name some. So, this will give you the rules for naming them. A prefix is added to the name of the alkane. It depends on what halogens are attached. The prefixes for the 4 different halogens, I think you've worked out what they are already. But essentially, you take off the INE and you put an O instead. Okay, so you get fluoro, chloro, bromo, iodo. Iodo looks kind of weird as a prefix. Are you making jokes at Julia's expense? Are you going to start calling her iodo? What is? I see, okay. Alright, and we also possibly need prefixes for the number of atoms. And this one we should know already as well. So we've got, there's no prefix for 1, but then 2 is di, 3 is tri, 4 is tetra, and 5 is penta. Exactly. And then we use numbers where necessary. Only if they're necessary do we use numbers to indicate to which carbon atoms each halogen is attached. Yes?
So when is it necessary to use numbers?
It's necessary to use numbers when without them you could have different versions of the same molecule. And it's kind of difficult to give you an exact rule on that. A lot of it comes from experience, from working out the names. Okay, I'll let you finish any notes you want to do on that for a sec. We haven't had that conversation yet. We haven't decided. Yes, yes, question.
So what comes first, the number of prefix or the column?
That's a good question, actually. Yeah. So which prefix comes first? Well, you would need the prefix for the number of halogens before the name of the halogen. So it'd have to be like dibromo or trichloro. Okay. And usually, folks, if you've got more than one halogen, one type of halogen, normally we put it in alphabetical order. So bromo would come before chloro, but chloro would come before fluoro. That would be my normal rule, okay? So alphabetical order if you've got different halogens. Yeah, that's exactly what it says in the book. If there are 2 or more different halogens, then their prefixes appear in alphabetical order. So, ready? Not ready yet? You okay, Pranesh?
Yes.
Good. You always look scared when I ask you that. Don't be scared. Oh. Okay, you ready to see if we can name some things? Let's do it. Okay, that's a nice easy one. I've got the type in the name of the structure below. And hopefully get it right. So, who's going to help us out with a name for that one first? Is that you, Leanne, or are you scratching your back? Go on, give it a go. Fluoroethane. Let's have a look. Fluoroethane. If we check, yay, you got a tick. Well done. Okay, now they get harder. No, that's not too bad, that one. Who's going to do a name for that one for me? Bismarins. Cool. Say again? Chloro Propane. Let's have a look. Not quite. Huh? What do I need to do? One. It needs to be one chloropropane because you could have two chloropropane, which would be different. Okay? With the chloro on the middle carbon atom. So, number 3. Somebody else this time. Julia? Dibromoethane. Let's have a look. D-I-B. Ooh. Dibromoethane. Huh? 1, 2. Dibromoethane. There you go. Check. Got to have the numbers on it because it could be 1, 1. Dibromoethane. You can have two bromines on the same carbon atom. Yeah.
Question. But if you flip it, wouldn't it look the same?
But if you, yeah, I mean yes, you can flip this around, it would always be the same. But if I move this bromine to here, then it would be a completely different one. That would be 1 dibromo ethane. Okay. Now we're getting the hang of where the numbers go. What are we going to go for here? Someone else who's not done one yet? Ziad, did you do one already? No, you didn't.
1 chloro to 1 iodo.
So 1. Oh, sorry, I didn't tap there. 1 chloro, 2 iodo ethane. Good work. Well, it's got 1 chlorine and 1 iodine. So if it's 2 of the same, then you would need di with it. Exactly. Okay. Let's try this one. Who's feeling brave on this one? Only one brave person so far. Pranesh, fantastic. Thank you for volunteering. Let's see what you got.
1, 2, 3. Try chloro.
1, 2, 3. Try chloro.
1.
1
Bromo.
bromo.
Propane.
Propane. Let's have a look. Oh, it's giving me a cross there. How might we change it? We'll see what actually comes up. James?
You're supposed to have it in alphabetic order, so it should be 1 bromo, 1, 2, 3, trichloro.
Okay, so if we put it in alphabetical order, then it would be 1 bromo. Do it like that, yeah. Let's see, check. Ah, exactly, alphabetical order. So 1 bromo, 1, 2, 3 trichloro propane. Perfect. Okay. Any questions on how we name stuff in that case? No? Jemima?
So you know that you have like dashes like that, you have that like in your text and stuff, you always have dashes.
They do. You don't have to worry about the dashes particularly. You should use the commas in between the numbers, otherwise it looks a bit odd.
Yeah.
But the dashes are not that important, to be honest, and no one's going to mark you down if there's not a dash there. Okay. All right. So.
So this topic is important, like it's 6th grade resource assessment, right?
Yeah, because you've still got a week next week to do revision, so yeah. So, we have touched on this quite a bit now, and you should understand this, I hope. We've done a bit of primary, secondary, and tertiary, so that really does apply to halogenoalkanes. What we've not done, and we've only maybe touched on briefly, is that a chain of carbon atoms can be represented by R when we draw the structure. And quite often you even see it referred to as this in exams, as an R group. An R group can basically be any kind of little chain. Yeah? So essentially, a primary halogenoalkane has one R group, or the primary has a carbon attached to one other carbon. Secondary has 2 R groups, or the carbon is attached to 2 other carbons. And then tertiary has 3 R groups. So the carbon that the halogen is attached to 3 other carbons. Slightly different way of defining it from what we've done in the past. Jemima. So the 1 degree is just like a shorthand for primary.
Oh, okay. So can you write that in the exam and do the primary brackets and then continue writing your degree?
I would write the words just to make sure that it's primary, secondary, and tertiary.
So if you have R1, is that still second?
We would normally write it as different R groups, even if they were exactly the same, I guess. But they could be exactly the same. Okay, lots of writing going on. What's next? The X is the halogen.
I hate when you put so much in
Okay, you ready? It's okay if I change the slides? Do you need me to go back to the slides?
Yes.
Come on, hurry up.
Thank you, sir.
Remember, you don't need to copy every single word that's on there, you need to just summarize.
Okay, thank you, sir.
It is my pleasure. Genevieve, you okay? Maria, you alright? A few more seconds.
Yeah, no, it's
Sure? Okay. Alright, let's try then. All you've got to do is 7 structures. We've got to identify whether they are primary, secondary, tertiary, and people that have not actually spoken to me yet need to speak to me. So I'm going to pick on Genevieve first, and you need to decide, is that primary or secondary? Not quite primary. What do you think it actually is though, Genevieve? You've got a 50-50 chance now. I know, it's pressure. Huh? You think tertiary? It's secondary. Let's have a look just for a second why that is the case. Okay, we've got, this is your halogen here. Okay, looking at this carbon, okay, you could say it's attached to 2 different R groups, 2 different carbon chains, or that carbon itself is attached to 2 other carbons. Okay, that's what makes it secondary. Yeah. Essentially, I like to define it more in terms of how many carbons that particular carbon that the halogen is attached to, how many carbons are joined to it. So if it's only joined to 1 other carbon, it's primary. If it's joined to 2 others, it's secondary. If it's joined to 3 others, then it is tertiary. Let's have a look there. So, this one, who's still not spoken to me yet. Abdullah. Tertiary. You sound very confident. Why is that not? Yeah, that's good. Why is that not giving me a tick? I can tell you're actually right, but something along the way has gone a little bit wrong with that. I don't want to reset it because it's going to put it all in order. Okay, let's try again. So that was... Yeah, it's all actually broken now. Well, I'll just tell you the answers when you get them right. You were right. It was tertiary. Okay, if I just go back 1. That is tertiary because that carbon there is attached to 3 other carbons. Yes, Ahmed, you got a question?
Oh, you just answered.
Oh, okay.
So how do you know which carbon atom you're looking at?
Because this is the one attached to the halogen. Yeah? So, number 3. Ni. Primary. You are correct. Don't know why it's not ticking, but it is correct, okay? It's the carbon at the end of the chain, or that carbon is joined to 1 other, or the carbon only has 1 R group. Whichever way you want to look at it, it's primary. Who else now? Angie. Primary. You are correct, even though it won't tick for me. Doesn't like me anymore. Primary is correct. It's at the end of the chain. It's got 1 R group. It's joined to 1 other carbon atom. And all of those things. Okay, that's an interesting one there. Gabby. Secondary. You are correct. That one is secondary. You're kind of, your eye is drawn though. Be careful. Because your eye gets drawn to this area here. And you're like, oh, that looks like it could be tertiary. And yes, if it was attached onto this carbon atom, it would be tertiary, but it's attached over here. Okay, so it's only a secondary. Be careful you don't get caught out by little things like that. Again, another one to potentially catch you out. Bismuth.
Secondary. No, primary.
Which one?
Primary.
Primary. Okay, it is primary. You're right. So the reason being this, again, your eye is kind of drawn up to here, and you're like, oh, there's a branch. Is that really going to be? Is it going to be secondary? Is it going to be tertiary? But actually, it's at the end of the chain, and so it is primary. Okay, there's only one more left. Should be a nice and easy one to pick. This one's up for grabs. You did one already, so everyone said something already today. Maria, have you done one? No, go on, it's your turn then. Tertiary. You are correct. It is tertiary, okay. That carbon joined to 3 others. Fantastic. Yay. Happy days. All right. We are not going to look at the rest of that today. What time is it though? Yeah. Let's pause for a moment. Let's carry this on for a little bit away from the PowerPoint now. Halogenoalkanes are quite reactive compounds. I reckon you can already, from your stunning chemical knowledge that you have, you can probably already predict why halogenoalkanes might be more reactive than just alkanes are. Okay, if I draw in nice chloromethane, okay, what should I also draw on that diagram? Or what could I draw on that diagram to represent it even more accurately, I guess? Jemima? The electronegativity, kind of, yeah. But what would I be drawing on there?
I don't know what to call it, but I know delta positive.
Exactly. I want the partial charges on it, yeah. So the delta positive and the delta negative. Okay. So what is delta negative in that case? The chlorine, exactly. Okay. And therefore this must be delta positive. So if I add to this, you might want to add that to your notes, up to you. Quite noisy. And actually a point to make, and maybe to bring back to some of the answers I've seen in your tests, okay? When we're talking about electronegativity, please make sure that you get into the habit of talking about the difference in electronegativity. That's what's important, okay? So the only reason that there's a dipole here is not because this is electronegative or highly electronegative, it's because it's more electronegative than carbon, and so it pulls electrons towards it. So we really want to talk about that difference there. Okay? And because of the difference, that carbon-halogen bond has a permanent dipole. Okay? And it's that makes it more reactive. It's that makes it more susceptible to attack. In fact, it's not this bit that gets attacked. It's going to be the carbon that is susceptible to attack. Okay, in fact, we've already thought about, haven't we? Things that are attracted to areas of high electron density, what were they called? Electrophiles, exactly. So there's an opposite to that. Things that are attracted to areas of low electron density or positive areas are called nucleophiles, exactly. Okay, it's the opposite of an electrophile is a nucleophile. So these bonds can be attacked by nucleophiles. So nucleophiles give it a definition as well. Nucleophiles love the nucleus, or just positive areas in general. That's what a nucleophile does. We will give it a much nicer, broader definition than that when we actually look at the mechanism. But hopefully you've already come to the conclusion that our next mechanism will have nucleophilic in it. In fact, it's still actually, it's right there on my PowerPoint slide still. It's the title of one of the sections, nucleophilic substitution. Okay, but we're not going to go on to that today.
Sir.
Yes, Ahmed.
Just like a quick question.
Go on.
So that's nucleophilics attack, nucleophiles attack the carbon bond. Wouldn't it break the carbon halogen?
It would, yes. And if it breaks that bond and replaces it with something else, what kind of reaction might that make it? If you replace something.
Nucleophilic substitution.
There you go, nucleophilic substitution. Excellent work. Well, we've had electrophilic addition.
Substitution.
That this is going to be substitution. Addition with a double bond and breaking the double bond. Substitution is replacing a group with something else. Yeah?
It'll be fun.
It is going to be fun. Don't worry about that. We'll love the fun. Maybe Okay, so just to reiterate, our core practical will be about the rate of hydrolysis of different halogenoalkanes. Your task right now, because it's one of the criteria assessed, is to do a little bit of research yourself. Find out which type of halogenoalkane will hydrolyze the quickest. Chloro, bromo, or iodo. Primary, secondary, or tertiary. Do some research. If you look at a website, you may as well copy the addresses now and the name of the page, okay? Find out about it.